calculations, and I'll be waiting answers from you. So you need to calculate, and all right. So get ready. You will not be silent listeners, but you will also be actively participating in the discussions and calculations. All right. Okay. So with that, now shall I start recording? Okay, I'll start recording. All right. So in the last session, we have seen the thick wall cylinders. We can define two types of stresses. So one is the radial stress, and the other one is the circumferential stress. Okay, so you can see sigma theta is the circumferential stress and sigma r is the radial stress. So we can get expressions by the linear equations known as the Lamé solution. So we get expressions for the radial stress and tangential stress for thick wall cylinders. So you need to know for thick wall cylinders that they are the pressurized vessels, so they are mainly to carry pressurized liquids. Okay, so there will be inner radius and outer radius. So there will be inner pressure due to the fluids, and the outer pressure PO is the atmospheric pressure. Okay, so in most cases we can treat atmospheric pressure as zero because atmospheric pressure is uniformly affecting the outer outer side of the cylinder. All right. So at any point inside this thick wall cylinder, the distance is represented with r. So these are the things you should know. Then you can identify, you can appreciate the formula for the radial stress and tangential stress. So you can see everything is in terms of inner radius, inner pressure, outer pressure, and where you are calculating the stresses. So that is R. So this R is a variable within the uh, thick wall cylinder. So R can vary from inner radius to outer radius. So it can be anywhere in between inner radius to outer radius. So that's where you are calculating the radial stress and tangential stress. Okay, so generally the plot of the radial stress and tangential stress can be shown. You may just focus on this figure. Okay, so you can see this figure. So generally the inner radius, okay, the radial stress is maximum and is equivalent to the pressure, inner pressure Pi. Okay, and as a rule, the at the outer radius, so the radial stress will be zero. Okay, so at the outer radius, the radial stress will be zero. Whereas the tangential stress is maximum at the inner radius, sigma theta maximum, and at the outer radius, it will still retain some value. So it will not be zero. The tangential stress will not be zero at the outer radius. So we can define the average tangential stress. So we have seen that in the last session, average tangential stress will be, we can write pi ri in over the thickness. So the thickness of the cylinder will be RO outer radius minus inner radius. So this will be the average tangential stress. RO minus Ri is the thickness of the cylinder. So now we look into some important formulae related to the thick wall cylinders. Okay, so we'll be seeing the maximum shear stress, tau max, can be written as half sigma theta minus sigma r. So the half of tangential stress minus radial stress. So you can see we are only taking the magnitude, so we ignore the sign. So shear stress will be always taken as positive. So shear stress can also be written as okay, C2 over R square. Okay, so this once you substitute C2 over R square, so the maximum shear stress can be uh, given like this. So C1, C2 you can refer in the previous slide here. So C1 will be this portion Okay, so this is C1 and this will be C2. Okay, so you can just include except R everything in C2. Okay, so it's easy to see what is meant by C1 and what is meant by C2. So once you substitute the values, now the maximum shear stress can be written like this. So this is the maximum shear stress. And the maximum shear stress can also be in terms of yield stress. Let us see will in the next slide. So in terms of the yield stress, so you can write the maximum shear stress like this, sigma y over 2. So this is the yield stress at extreme conditions. So that means once the material is just crossing the elastic limit and started yielding. So that will be your yield stress. So the shear stress, maximum shear stress can be written as sigma y over 2. And once you substitute that is C2, okay, the formula becomes RO square RI square over RO square minus RI square, then P naught minus PI. So we take only the magnitude here. Okay, we ignore the sign. So sometimes P naught can be taken as 0. So in such a case, it will be simply, you can cancel this RI square, and it will be RO square into PI over, okay. So this is known as the nonlinear elastic stress distribution. So the maximum shear stress can be equated like this. Okay, then the same formula, so that means the nonlinear elastic distribution at extreme conditions, that means in terms of yield stress, can be given, the radial stress can be given when the inner pressure is greater than outer pressure. So this is the formula for the radial stress in terms of yield stress when the inside pressure is greater than outside pressure. Okay, so the tangential stress is given like this. Okay, so this formula is important. Okay, these two formulas you need not worry. Okay, so next we see the elastic plastic behavior. Uh, okay, considering the plastic thick wall cylinders. So we study when the thick wall cylinder is completely under plastic conditions. Okay, when the thick wall cylinder is completely under plastic conditions, then the governing equation we can write it as that d sigma r over dr. So this is how the radial stress varies with the radius plus sigma r minus sigma theta over r. So this should be 0 for equilibrium conditions. So some of the forces and some of the movements acting on the system must be 0. So by applying this for plastic behavior, we can write this expression. Now, once you simplify this expression, so the resulting equation will be the radial stress in terms of the plastic yield stress, sigma yp ln r plus c. So here R represents the position inside this thick cylinder, where you're calculating the radial stress. So this R can be any point within the thick cylinder. So this equation is known as the nonlinear plastic stress distribution. So where you're calculating the radial stress. So we can apply the boundary conditions. So boundary conditions means when the R you're calculating at inner radius. So that means you're calculating, let us say, the radial stress at the inner radius. Then you can say that you can prove from this expression that the radial stress is equal to negative of inner pressure. So the radial stress is equal to negative of inner pressure. Then at the outer radius, so the radial stress is equal to negative of outer pressure, PO. Okay, so here this is an important expression which we know as nonlinear plastic stress distribution. Okay, so this is how you can see when the inner radius, you can see the entire thick wall cylinder is under plastic condition. So the entire thing is under plastic condition. So this is all under this plastic condition. So when outer pressure is zero, so the atmospheric pressure is considered as, because it's uniformly acting on the entire surface of the cylinder, so we can consider it as zero. So therefore, the radial stress can be written like this, and the tangential stress can be written like this. So here, sigma yp is the plastic yield stress. Okay. So R is where inside the cylinder where you're calculating the radial stress and tangential stress. So these two formulas are important. So these are for the uh, nonlinear plastic distribution expressions for radial stress and tangential stress. So now you can see how we represent these stresses on a cross section. So you can consider this as your inner radius, Ri. So let us say this is your outer radius. Okay. So the radial stress sigma R will be zero at the inner radius. It will be zero at the inner radius. I'm sorry, it will be equivalent to the inner pressure Pi. So which is maximum, and the radial stress is equivalent to Pi, and it gradually decreases at the outer, it will be zero, even when the material is fully plastic conditions. Okay. Whereas the circumferential stress, so you can see it will be maximum at the inner radius and gradually decreases at the outer radius. It still will retain some. So this is normally under elastic conditions. Under fully plastic conditions, what happens is um, the radial stress behavior will not change. So it is equivalent to negative pressure, internal pressure. At the outer radius, it will be zero. Whereas the tangential stress is having, it's not maximum at the inner radius, but it will be maximum at the outer radius, and it gradually increases. Okay, so this is under fully plastic conditions. So the next one is we'll see under elastic plastic behavior. So when the thick wall cylinder is partly elastic and partly plastic. So you know that as the pressure increases, the yielding of the material starts from the inner part of the cylinder. So consider that the all this part is under plastic. Okay, so this is plastic inside. Okay, and outer is elastic. So that means the thick wall cylinder is partly under plastic conditions and partly under elastic conditions. So the region outer closer to the outer radius will be under elastic, and the region closer to the inner radius will be plastic, because the yielding starts or commences mainly from the inner cylinder. Okay, so now you can, under these conditions, when the thick wall cylinder is partly elastic and partly plastic, so then we can see the formulations related to the, okay, so you can write Pi minus Po. Okay, so this is for the elastic part. So you can write in terms of the yield stress here, sigma y. Okay, so the whole thing you can write. So this is the formula for the plastic behavior. So for the plastic part, X can be replaced with P naught. So because P naught is equal to X, so P naught minus Pi can be written as, so this is the same formula which we have seen for elastic conditions. Okay, so this, I'm sorry, for the plastic behavior. So for the elastic conditions, so this formula is there. So these are the expressions when the material is undergoing partly elastic deformation and partly plastic deformation. So essentially, we are talking about three conditions. One is the yielding condition. Next one, when the thick wall cylinder is fully plastic. And the other condition is when the thick wall cylinder is partly elastic and partly plastic. So in all the three cases, so we are writing expressions for the radial stress and tangential stress. So in terms of the yield stress or in terms of the plastic yield stress. So all this will be, yeah. So you can see here the representation when the system is part of the cylinder is under plastic and partly under elastic. Okay. So this is how the radial stress and tangential stress will change. Okay. Um, so you can see under two categories here. Okay, so this is B. Okay, so you can see the tangential stress increases, okay, till the plastic limit. Okay, so this is how the elastic limit the behavior. Okay, so the radial stress will be just gradually decreases. Okay, so in these conditions, so you can use these expressions to calculate the radial stress and tangential stress. Okay, so here ABCs are defined here. So ABCs refers to the thicknesses of the elastic part and plastic part. All right. So the next one is the linear approximation. So Lamè's equations are nonlinear approximation. So for linear approximation, you can see this is using Lamè's equations. Okay. So for elastic behavior, the average stress, we can write it as Pi Ri over the thickness, Rho minus Ri. Okay, so this is for the elastic behavior under linear approximation. Okay, so we can say that the radial stress, okay, at the inner radius, R is equal to Ri. Okay, so the tangential stress can be given as sigma theta, which is sigma average plus Pi over 2. So you can see these are the important expressions here. Okay, so this is for uh, linear approximation, elastic behavior. Okay, so sigma theta can be written as sigma average plus Pi over 2. What is sigma average? Sigma average is Pi Ri over Rho minus Ri. Rho minus Ri is just the thickness of the cylinder. Okay, then the same thing at the outer radius. So you can write the average tangential stress is sigma theta. We can write it as sigma average minus Pi, that is inner pressure, over 2. So this is for linear approximation, elastic behavior. Then plastic behavior, you can have the same thing. So for plastic behavior, the average stress will be the same. So average stress will be the same. Then you can write sigma theta minus sigma r is your shear stress. But essentially, you can say at inner radius, the average tangential stress sigma theta will be sigma average minus inner pressure over 2. Sorry. Then at the outer radius, you can say the tangential stress will be sigma average plus inner pressure over 2. So what is that we can learn from here is that, okay, I'm sorry. We can define for thick wall cylinder two types of formulation. One is non-linear and the other one is using a linear formulation. So this is based on linear formulation for elastic behavior and plastic behavior. So for nonlinear, we have seen the expressions for nonlinear. Okay, so this all these expressions are nonlinear. So this is for nonlinear fully plastic stress distribution. So the radial stress is can be calculated from this formula. The same thing we can see, okay, here. So for fully plastic behavior, so nonlinear formulation. Okay, so this is for elastic plastic conditions for nonlinear formulation. So this is for the plastic part, and this is for the elastic part. So basically, in thick wall cylinders, we can study how to calculate the radial stress and tangential stresses under different conditions using a linear formulation and nonlinear formulation. So all the formulas are in terms of inner pressure, inner radius, outer radius, and where you're calculating, that is in terms of r, small r. Okay. Now, in the last session, I think we have done some calculations, some parts. Then there are two more important formula problems in this topic. So let us look into those problems. So I just skip this one, we have done. So now let us look here. This is the problem related to designing a thick wall cylinder. So you are asked to design a thick wall cylinder, okay, 80 internal diameter for an internal pressure of 80 megapascals, okay. So such as to provide a safety factor of 3.0. This safety factor for against yielding, okay, in the cylinder, and the factor of safety 4.0 for ultimate collapse. Okay, there are two safety factors. One is 3.0 for yielding and 4.0 for ultimate collapse. So the yield stress of the material is 400 megapascals. Okay, so this is the yield stress of the materials. So now you're asked to use both linear and nonlinear stress distribution methods of calculation. So basically, you're asked to design a thick wall cylinder. So we know the internal diameter, so that means you know internal radius. Okay, so internal radius is 40 mm, right? It is given. We also know the yield stress, and we also know the safety factors for yielding, and also safety factor for ultimate collapse. And also we know the yield stress of the material, okay? 400 megapascals is given. So we need to design the thick wall cylinder. So that means, so guys, let me tell, can someone tell me what is that we need to calculate here? So this is internal pressure, PI. Can someone tell me what is that we need to calculate here? No, outer pressure will be always atmospheric pressure. So outer pressure is not a criterion when we discuss thick wall cylinders. So you take any pressure vessel, the outer pressure is always the atmospheric pressure, right? So these thick wall cylinders are basically used as pressure vessels to carry fluids. So therefore, the outer pressure is not part of the design of a thick wall cylinder. Uh, the wall thickness. Indirectly, it is simply the outer radius. So you need to calculate the outer radius. So your design constraint is that you need to maintain an inner radius of 40 mm. So then to design a thick wall cylinder which can have 80 megapascals pressure, Okay, and there are some safety yield safety factors, and the safety yield of the material is 400 megapascals. So to design means you need to find out what will be the outer radius. All right, so you need to calculate the outer radius in this case. So the given material is the inner radius is given, the inner pressure is given, then the safety given 400 megapascals, and there are a couple of safety factors here. All right. So this type of question will be a potential exam question. So normally the first two questions will never be asked in the exams. So this question and the next question which we'll be doing will be important questions for the exams. All right. So guys, just write down whatever is the given material, then uh, we'll try to solve this problem. So I'll be capturing your attendance. Give me a minute. All right. So hope you have taken down the given data. So then I'll move on to the camera now. So what's given now? So we can say that the given information is internal diameter, internal radius. So Ri, you can say 40 mm. Okay. So sigma y is given 400 megapascals. And what else? The internal pressure is given 80 megapascals. Okay. So the safety factor for yielding is given. So safety factor for yielding. So this is 3.0. Then safety factor for ultimate yield stress. So this is 4.0. Okay. So you can calculate what is the ultimate yield stress. So ultimate yield stress will be, any idea what will be the ultimate yield stress? So 400 times 4.0. So you will get 1200 megapascals. So this will be the ultimate yield stress. So now you need to apply the safety factor for yielding. So you can say that for plastic yielding, safety factor will be, so ultimate yield stress over okay. So the safety factor 3.0. So that means so you can say 1200 over 3.0. So that is 400. I'm sorry. Okay. I'm sorry. You need to use 4.0. This one is 3. Sorry. So safety factor for yielding. Okay. So the yield stress will be 400 into 3.0. So that will be 1200 megapascals. Then ultimate yield stress will be, so this 1200 over 4.0. So that is the safety factor for ultimate yielding. So that gives you 300 megapascals. Okay, so that means actually you need to reduce from 400 to 300 megapascals considering the safety factors. So now your sigma yp will be plastic yield stress will be, we can take it as 300 megapascals. So this is the additional information now we can interpret from the given description of the problem. So now to design the cylinder means so we need to find out the outer radius. And the question asks you to find out outer radius under different formulations. Okay, so different formulations means nonlinear, then elastic, nonlinear plastic, then linear elastic and linear plastic. So we have to look for these four: nonlinear, elastic distribution, so then nonlinear plastic distribution, then we need to go for a linear elastic, so then linear plastic. So we need to do for all these four stress distributions: nonlinear elastic, nonlinear plastic, so linear elastic and linear plastic. So we'll try to apply the required equations, and we have all the data except outer radius, so we can find out outer radius. All right, guys, any questions? I'll take this out. Okay. What is the sigma, Eva? Sigma yp is the plastic yield stress. Okay, for yielding, we need to take 3.0. For ultimate yielding, 4.0. So to get the ultimate yield stress, so for yielding, we multiply with 3.0, so you get 1200 megapascals. Then for plastic yield stress, okay, then we use the ultimate yield stress over the ultimate yielding safety factor. So that gives you the plastic yield stress as 300 megapascals. All right. So, so normally in many problems, they straight away give you the plastic yield stress. But here you need to calculate based on the safety factors given. Okay. So first let us do this for nonlinear elastic. So for nonlinear elastic. So nonlinear elastic formulation. So under this, the maximum shear stress is half of plastic yield stress. Okay, so the formula for this is Rho square Ri square over Rho square minus Ri square. So this is magnitude only P0 minus Pi over R square. Okay, so here we can consider outer pressure is equal to 0. Okay, and R is equal to Ri. So we are taking the variable R as internal radius. So in this case, we can write sigma yp over 2 is equal to, okay, so if you replace this with Ri, okay, this Ri square will be cancelled. Okay, I can write this as I can replace this with Ri square. So we can cancel out this. Okay, so that gives you RO square. Okay, so you're only taking the magnitude of this. So negative PI over RO square minus RI square. Okay, so sigma YP is 300 over 2. So we need to calculate RO square. So PI is given 80. Okay, RO square 80 megapascals. Okay, RO square minus RI square. So RI is given as 40 mm, right? Yeah. So we can say 40 mm square. So the only unknown is RO. So calculate and let me know what is the outer radius under nonlinear formulation. I'll give you 2-3 minutes. No, Eva, that's not correct. Can you check again? That's correct, CD Chang. And Daryl, no. So the outer radius you will be getting about 58.55 mm. Okay, so this is the diameter which will radius which you propose when you're dealing with nonlinear elastic formulation. So for nonlinear plastic formulation, so you can uh, do the calculation again. Okay, so when we consider nonlinear plastic formulation, so for nonlinear plastic formulation, you can refer the expression, the corresponding equation for a radial stress. So radial stress can be given in terms of plastic yield stress ln R over RO. So this is the expression for the radial stress under nonlinear plastic formulation. Okay. So here we know that the radial stress is equal to the negative of internal pressure. Okay, when R is equal to Ri, internal radius. So at internal radius, so the radial stress is equal to negative of internal pressure. So we can apply now. So negative 80. So sigma Yp is, we know, 300. Now we replace R with Ri. Okay, Ri we know is 40 over Ro. So now solve this and find out under non-linear plastic formulation. So what will be the outer radius? So I give you a couple of minutes for this calculation. That's correct, Shafiruddin. Thank you. So you will get about 52.22 mm. Okay, so this is using the nonlinear plastic formulation. Okay, so we have done both the nonlinear elastic and the plastic. Then we move to nonlinear, linear elastic and linear plastic. Okay, can I take this out? Can I take this paper out? All right, thank you. No, okay, Azar. All right, so next we look into the third part, so which is a linear elastic. Okay? So linear elastic formulation. So for linear elastic formulation, so we know the sigma yp over 2 can be given as sigma theta minus sigma r over 2. So this means that sigma yp is sigma theta minus sigma r. Okay? But we know sigma theta is okay, sigma average mine plus pi over 2. So this is the formula for the linear elastic formulation. Okay? So this is for the linear elastic formulation. So now here we substitute okay. So sigma average we substitute pi ri over ro minus ri, the thickness. So we can write now sigma theta is equal to, okay, so we write in terms of sigma yp. So we know sigma, okay, sigma yp is equal to, so we replace sigma theta, sigma average value, so which is pi ri over ro minus ri, okay, then plus pi by 2, okay, minus sigma r. Okay, So sigma R is equal into internal pressure. So we can write minus sigma R is negative pi. So sigma yp is sigma theta minus sigma r, but sigma theta is this. So sigma yp will be sigma average plus pi by 2 minus sigma r. Okay, so we write sigma yp is equal to sigma average plus pi by 2 minus sigma r. Sigma r is at internal radius is equivalent to negative of internal pressure. So minus of minus pi. So sigma yp is now we know the value. Okay, so sigma yp is so pi internal pressure we know 80 megapascals. Ri we know 40 mm. So Ro minus 40 plus pi over 2. So pi over 2 is 80 over 2. I'm sorry, pi, yeah, 80 megapascals over 2. Minus of minus pi becomes plus pi. So can you find out what is Ro? So guys, you can calculate from this outer radius. So this is for linear elastic formulation. So let me know your answer once you calculate. That's correct, Dicheng. See Dicheng here. So you can write 57.77 or 78, both are okay. So this is the outer radius as we can get for linear elastic formulation. So then the next part will be the linear plastic. So for linear plastic, so we can write again same thing, sigma theta, sigma yp will be sigma theta minus sigma r. But for linear formulation, for linear plastic, so we can write sigma theta is equal to sigma average minus pi over 2. So this is the formula for linear plastic. Okay. So now we can write sigma yp is equal to sigma average minus pi over 2. So sigma r is equivalent to internal pressure at r is equal to ri. So we can write minus sigma r means minus pi. Okay, so we can write 300. So sigma average again the same thing. So we can write pi ri over ro minus ri. So this is sigma average. So we write the pi internal pressure 80, ri 40. So RO minus 40, pi by 2 is minus 40, so this will be plus 80. So calculate outer radius. Sorry. So let me know your answer, guys. 54.55. Can you recalculate, Shafaruddin? Yeah, I think 52.31 is correct. So you can say that 52.31 mm. Okay, so like this, you will be able to design the outer radius, or okay, find out what will be the outer radius under different formulations. Linear elastic, linear plastic, then non-linear elastic and non-linear plastic. So you can see all formulations. So the minimum value is about 50.78 and the maximum value is for non-linear elastic formulation. So 58.55. All right, so this is how this type of problems can be solved. Guys, any questions? Otherwise, I'll move on to the last question of under thick wall cylinders. Online CD chain. So I take out this, then we move on to the next question. So for the next part, please take note that this type of question is a potential end of term exam question. So both question 3, question 4 are important questions for end of term exams. Okay. All right. So this is the next question, similar to your assignment question. Okay, here we are dealing with a thick wall cylinder. So the internal diameter is given. So that means you know internal radius. And yeah, external diameter is given. So you know RO. So RI, RO known. Okay, RO known. It is loaded by internal pressure. So we don't know internal pressure. The yield strength of the material is given directly 400 megapascals. So now in all these problems, so you're asked to calculate the internal pressure required. So PI to initiate yielding in the cylinder. Okay. So using Lame's formulation. So using Lame's equations. Okay. So that is where you have C1 is sigma, CR is, sigma R is C1 plus. Okay, the Lame's equations we have seen earlier, so you need to use those equations. Okay, and sketch the stress distribution. So not only you need to calculate PI, but you also need to find out what is the radial stress and what is the tangential stress using the Lame's equations, and then show the distribution, how the stress varies. Okay, so that is the first part. And the first part is for initiate yielding, okay, for elastic conditions. Now for the plastic limit pressure, when the cylinder is fully plastic using nonlinear formulation. So again, using nonlinear formulation, when the cylinder is fully plastic, then sketch the stress distribution. Then part C is compare the results obtained from part A and B with those obtained when a linear stress distribution throughout the wall thickness is assumed. The last part is assuming a linear distribution. Okay, so calculate the residual stresses when the plastic pressure is applied and then removed. So here we need to calculate the residual stresses. All right, so read the problem, try to understand what is given and what is that we need to calculate. So here we know the yield strength of the material, 400 megapascals. So we know inner radius and outer radius. Then you need to calculate the, uh, for the part A, you need to calculate the internal pressure for yielding, and also need to calculate the radial stress and tangential stress to sketch the stress distribution. So whenever you have sketched the stress distribution means you need to calculate the radial stress and the tangential stress. All right. So here again we have the Laplace equations and nonlinear linear formulation. So Laplace equation refers to nonlinear formulation. All right. So I will go to the camera. So first we'll write down whatever is the given material, given information. So what is given? So we know the yield stress is 400 megapascals, and we know the internal radius is, I'm just taking down by 2, so 100 mm. So this is outer radius. So the inner radius is 25. Okay, so this is the given information. So now to initiate yielding, so we need to apply the Laplace formulation. So to initiate okay, so we need to apply the Laplace equations. So here it is simple. Sigma y over 2 is equal to, so pi rho square over rho square minus ri square. Okay, so calculate now. Sigma y is given 400, so sigma y over 2 is 200 megapascals. So pi need to calculate, then rho square is 100 mm square. Okay, 100 square minus 25 square. Okay. So solving this, you can find out internal pressure. So guys, let me know how much you get internal pressure. Yeah, 187.5. That's correct. No, Raja. 187.5 megapascals. So this is the internal pressure, PI. So once you get internal pressure, then you can calculate radial stress sigma R. So when you calculate radial stress, so you need to calculate the radial stress at inner radius, okay, the radial stress at the outer radius. So we know that at the inner radius, the maximum radial stress will be negative of the pressure. So we know this is 187.5 megapascals. And we know at the outer radius, it will be 0. Okay, so the radial stress is straightforward. Then the sigma theta tangential stress. So same thing, you need to do this for inner radius and outer radius. So sigma theta outer radius. So here you have to use the equations to calculate. Okay, you can find these equations at the very first slide, second slide, and at thick wall cylinders. So I'll just write this. So pi ri square over rho square minus ri square. So this is for inner radius. Okay, so you can just write 1 plus rho square over ri square. Okay, so sigma theta, the tangential stress at the outer radius will be, so pi ri square over rho square minus ri square. Okay, so here, so 1 plus rho square over rho square, outer radius. So you can calculate now what will be sigma theta I and what will be sigma theta O outer radius. So just let me know once you calculate. Uh, the sigma theta, what's the doubt? 1 plus rho square. Yeah, that's correct because you are replacing the r with outer radius. So 1 plus 1 will be 2. Uh, 212.5 is correct, Navar, Ajay. So 212.5 megapascals. So here outer radius, That's correct, Azhar. So you will get 25 megapascals. Okay, so now you need to show the distribution. So you need to sketch the distribution. So how the so I can show this is outer radius or O. Okay, so let us say you can plot your radial stress first. So the radial stress at the inner radius is negative 187.5. So approximately, I'm just drawing 187.5. At the outer radius, it will be 0. So from here to here, so you can just join these two. Okay. So this is how the radial stress varies. So you can just show, okay, at the inner radius, okay, at the inner radius, it is negative 187.5 megapascals. So that is negative of the inner pressure. Okay, then at the outer radius, it will be 0. But when you come to the tangential stress, so tangential stress at inner radius is equivalent to, so you can say this will be 212.5 megapascals. So if you want to show, you can show above also, okay? And at the outer radius, it is 25, okay? So it just varies like this. Okay? Sigma theta 25 megapascals. Okay, you can show with a neat sketch something like this. Okay, so if you want to show the arrows upwards also, it is okay. So some figures, they just show upwards like this. The numerical values will be the same. Either way is all right. It is only just depicting the stress distribution within the thick cylinder, how the radial stress and tangential stress varies within the inner and outer radius. Okay, so once you calculate that is, the numerical values and just show approximately. Okay, so if the question asks you to draw the stress distribution, then you must plot this. So for assignment also, you must plot this and plot clearly. Okay, so plot in a legible fashion and neatly. Otherwise, you will be losing, fraction of marks. Is that clear, guys? Can I move to the next part? Now, this is elastic formulation for yielding. So we have to do the same thing, the nonlinear formulation for plastic. Okay, I take this out. Can I take this out? All right. Thank you. That's it. Okay, so the next one we do will be for a nonlinear formulation. A plastic. Okay, so for plastic nonlinear formulation, the radial stress, we can write it as sigma r is equal to sigma y ln r over R naught. Okay, so here sigma R is negative of internal pressure at R is equal to Ri. Okay, so we know this. Okay, now we substitute sigma R is equal to negative Pi. So sigma Y we know 400 ln. So here R becomes Ri. Ri will be 25. Ro is 100. So calculate what is the pressure Pi. It's 554.52. That's correct, Dichan. With a negative sign, right? So Pi, we can take the negative sign. So you will be getting about negative 554.5 megapascals. Okay. So we know the inner pressure due to plastic, okay, under nonlinear conditions. So now we can write the radial stress sigma r, okay, at inner radius is negative of pi. So you can write negative 554.5 megapascals. Okay, at the outer. Uh, Here, radial stress cannot be positive because radial stress is equivalent to pressure there. So sigma outer will be 0. Then we can calculate now the tangential stress. Okay, so sigma theta at inner radius. Okay, so here you can refer the formula for the plastic formulation for the tangential stress at the inner radius. So here it will be 1 plus ln Ri over Ro. Then sigma theta at the outer radius will be sigma y into 1 plus ln Ro plus over Ro. So you can calculate now both the tangential stress at inner radius and outer radius. Yes, no, as are correct. So you get negative Do you get negative? Both are positive, I think. 184.5 megapascals, and here you get about 400 megapascals. So both will be positive because you are taking the magnitude only. So whatever the sign, we ignore the sign, only take magnitude. Okay, so then you need to plot the stress distribution. So as was done in part A. So I skip the plotting the stress distribution. So I hope you can do this for your assignment. Is that okay, guys? So next we'll do linear formulation elastic. Okay, so here we write the sigma y is sigma theta minus sigma r. Okay. So, but sigma theta is sigma average plus pi over 2. So, this is the formula. Okay, so we can write this as sigma average plus pi over 2. So the radial stress is minus pi. So minus of minus pi, you will have plus pi. Sorry. So we can write sigma theta average plus 3pi over 2. So sigma y, we know the value, 400. Okay. So sigma theta average, you can so sigma average is pi ri over rho minus ri. So you can write pi ri plus, so calculate what is pi. So let me know your answers once you calculate. That's correct, Sage. So you can write 218.2 megapascals. So this is the pressure for linear formulation elastic. So linear formulation elastic. So now we have to do the same thing for a plastic, linear formulation for plastic. Okay, I take this out. So now we do linear formulation plastic. Okay, plastic. So here again, we write the same thing. Sigma theta is sigma r minus sigma y. Sorry. So sigma y is sigma theta minus sigma r. Okay. So, but sigma theta for plastic is sigma average plus pi over 2. So this is the formula for plastic. Okay, so we can write sigma average is same thing, pi ri over ro minus ri. All right, so now we substitute sigma y is equal to sigma average plus pi by 2. So minus pi. Okay, so you can write now pi ri. I'm sorry, I think I wrote the formula wrong. So this should be negative minus. Okay, so here should be negative here. Okay, so you can write negative pi over 2 plus pi. So you can write pi is unknown, ri is 25, ro minus ri, 100 minus 25, 75. So this will be plus pi by 2, plus 40. So this side you will have 300, 400. So solve for pi. What is your question, Hema? Sigma r is equal to negative pi, correct. So the radial stress is always equivalent to negative pi. So here sigma r you are taking at inner radius. So therefore it is equivalent to pi. Ro minus Ri is 100 minus 25, right? 100 minus 25 is 75. So you can see Ro is 100, Ri is 25. So therefore the difference is 75. So any answer for inner pressure? How to get the 40? So this is pi by 2 plus pi by 2, right? Pi minus pi by 2. Oh, I'm sorry. This should be, you need to calculate pi, right? So you need to write pi by 2. That's correct. So it's not 40, but it should be pi by 2. I'm sorry, accidentally I wrote it. So any final answer for the internal pressure? So this is for plastic. So you guys are taking longer time for this. Any answer, guys? Shafaruddin is correct. Nurazar, it's not correct. So you can check your calculation. So you get 480 megapascals. Okay. So this is part C. Okay. Then part D, I'll leave it to you. So how to draw the residual stress distributions. So we have done in one of the assignment earlier. So you can follow the same way. Then with that, I think we have completed all the things related to your second assignment. All right. So now the time is nearing 8:10. So we'll stop here. Then we'll have a break. Then we'll meet at 8:30. Then I'll go through one of the past year exam paper. Is that okay? So we'll have a break now. So we'll meet at 8:30. Then we'll go through one of the past year exam paper quickly. Okay. All right, guys. So you can have a break now. So I'll see you at 8:30 again. All right. How about others? Only in the. All right, Michael. So okay. All right. So I'll see you at 8:30 then. Have a break. Hi guys, hope you're back. All right, along. How about others? Yes, Azhar. Okay, Daryl, Michael. All right. All right. So we can. All right. So what I've done is, yes, Michael, I do record. Okay. So I just copied. I just scanned some of the one of the old question paper for your reference. Okay, so the question paper will be like this. So how many questions you can see here? There are three questions. All right, so each question, the number of marks will vary. So you can see that this question 4 will have two parts. So that means you will have already 5 questions. Then you have 2 questions here. So altogether there will be the 6 questions, but question 4 will have two parts. So you can consider there will be 7 questions. Out of that, you can see the last question is similar to what we have done just now. Okay, so this question is similar to what we have done now. So you have to complete all these questions in 3 hours, and yeah, to scan and upload, you may have additional time. But this will be a challenge because it involves a large amount of calculations. All right, now we'll go one by one question. Okay, let us look at the first question. So, guys, note down what is the strain tensor given there. Note down the strain tensor. Okay, so you're asked to do the characteristic equation for the strain in the three-dimensional state of stress. Okay, I'm looking at this question. Okay, so the strain tensor is there. So the first part, there are 4 parts. The Young's modulus is given, then the Poisson's ratio is given. So the first part is calculate the characteristic equation of strain for the three-dimensional state of strain. So that means you need to calculate J1, J2, the first invariant, second invariant, and the third invariant. So when you look at the determinant, you can see the bottom row is all zeros. So therefore, straight away you can see J3 will be 0. Okay, so now can you guys calculate what is J1 and J2? The first invariant and the second invariant. So J1 will be simply epsilon x, now the three normal strains minus 20 plus 0 over 3. So, so J1 will be negative 15. Of course, into 10 power minus 5. So please note down the strain tensor, then the elastic properties, the Young's modulus, and the Poisson's ratio. Then we'll try to work the first characteristic equation for the state of strain. Yeah, minus 5, right? So we need to write 15 into 10 power minus 5. Okay. Then we need to write the characteristic equation for the stress at the same point. Okay. Then calculate the volumetric strain and the deviatoric strain. Then calculate the mean stress and the deviatoric stress. So please note that there will be 20 marks for this type of question. All right, so I'll go back to the camera to okay, the given stress tensor is, so you can write 5, 25, 0, 25 minus 20, 0, 0, 0, 0 into 10 power minus 5. Okay, so the first one, the J1 characteristic, first strain invariant. So we need to add all the normal strain components. So 5 minus 20 plus 0 into 10 power minus 5. So you will get minus 15 into 10 power minus 5. So J2, so one good thing is, so you have 0, so you can simply write this as 5, 25, 25 minus 20. Okay, so plus you get 0 plus 0. Okay, so basically you get 5 into minus 20. Okay, can someone calculate and let me know the answer for this J2? And J3 will be 0. Minus 725 to the power. That's correct, but what will be the power? 10 power minus 10, because you're multiplying 5 with 5. So J2, you get a negative 725, 10 power minus 10. So then we can write the characteristic equation for strain. Okay, we can, the characteristic equation is epsilon cube minus J1 epsilon square plus J2 epsilon minus J3 is equal to 0. So this is the characteristic equation for the state of strain. So just substitute J1, J2, J3 values. So you get epsilon cube minus J1. So minus into minus plus. So you can write plus 15 into 10 power minus 5 epsilon square. Okay, plus J2 into epsilon. So minus 725. So I just take out this sign, minus 725 into 10 power minus 10 epsilon. So J3 is 0. So we can write the characteristic equation like this. So this will be negative here. Is that clear, guys? So this is how you can write the characteristic equation. And whenever the row is all zeros, so the determinant value will be 0. No need to show any calculation. Straight away, you can give the J3 as 0. Now, Part B, you have to calculate the state of stress. So characteristic equation for stress. So this is part B. Now, what we have is the strain tensor, and you know the properties, Young's modulus, and the uh, Poisson's ratio. So we need to apply the stress-strain relationships to convert the strain tensor into stress tensor. Now, to do that, first we need to calculate the rigidity modulus or the shear modulus G. So, which is E over 2 into 1 plus Poisson's ratio. And we can calculate the bulk modulus, which is Young's modulus over 3 into 1 minus 2 times Poisson's ratio. So guys, calculate these two and let me know your values. And the mean strain is so let me know the shear modulus and the bulk modulus values. Any answer for the rigidity modulus? G is 142.86. I think not correct, Shifruddin. Michael is correct, I think. Yeah, so G you get 76923 okay, megapascals. The other one is K is also correct, Michael's answer. So we write 166. So 56 megapascals. So you can find both the shear modulus and bulk modulus values like this, and also you can calculate the mean strain. So mean strain is simply the three normal strains over 3. So in other words, J1 over 3. So we have already calculated J1, so the mean strain you get. So now we need to apply the the relationship. Once we know the mean strain and the bulk modulus, then you can calculate uh, the mean stress. So the mean stress will be 3 times K times epsilon M. So this is the relationship between the mean stress, mean strain, and the bulk modulus K. So therefore, you will be able to calculate the mean stress. So can someone calculate and tell me? That's correct, Michael. So negative 25 megapascals. Okay, so once we know the mean stress and we know the mean strain, therefore we can calculate the deviatoric strain tensor. So I'll just take out this. Can I take this out? Okay, so now we can get the deviatoric strain tensor. So deviatoric strain tensor. So we can write epsilon dash. So this will be the given strain tensor minus the mean strain tensor. So the given strain tensor minus mean strain tensor. So the mean strain tensor is -5. So the first one is 5 minus of -5. So the first element will be 10. Okay. So the 5 minus 5. So 5 plus 5, 10. So the second element will be 25. Okay, so this one will not change. So this one will not change. So the -20 minus of -5. So -20 plus 5. So this one will be -15. So the other things will not change. So here the 0 minus 5. So it 0 minus -5. So 0 plus 5. So this will be your deviatoric strain tensor. Okay, so just the given strain tensor minus the mean strain tensor. So mean means only the diagonal value. So all other values will be 0. So we can write the mean strain tensor as -5, 0, 0, 0, -5, 0, 0, 0, -5. All right, so this is just to write the mean strain tensor in matrix format. So once we know the deviatoric strain tensor, then you can convert this deviatoric strain tensor into deviatoric stress tensor sigma dash. So this will be 2G. Okay, so it doesn't matter whether you put the dash below, inside or outside the square brackets. So you will be able to calculate the deviatoric stress tensor by multiplying the deviatoric strain tensor with 2 times G. So guys, can you tell me the values? So just multiply with 2G all the elements. So you can use megapascals here. So the G value is 76923 megapascal. So 2 times this value multiplied by each element into 10 power minus 5. So can someone give me the first value? So that is 2G times 10. 153.85, but I think the values are correct. But when you write in megapascals, it will be 15.38. That's correct, Daryl. So I think CD Cheng is also giving, all of you are giving the same values. So I can write this as 15.38. So how about the second one? Because the last one will be 0, the bottom ones will be 0. So can you give the second rows first? 38.46 correct, CDG. So the last one will be 0. How about second row first column? So it will come because 25, 25. So you can just write 38.46. So what will be no, these two will be the same because 25, 25. So whatever the value you get here, you also get the same thing. So can you calculate this value? That's correct, negative 23.08. Safaruddin is giving the second one. I got it, minus 23.08. That's correct. So then calculate the last one. Daryl, your value also correct. So just multiply with 2G. That's not correct, Safaruddin. Correct, yeah, that's correct. So you get 7.69. So this is the deviatoric stress tensor. So you get the deviatoric stress tensor. So once you know the deviatoric stress tensor and you know the mean stress, okay, so then you will be able to calculate the stress tensor. Sigma, the stress tensor will be the deviatoric stress tensor plus the mean stress tensor. Okay, so you know the deviatoric. So what is the mean strain tensor? So sigma m is we just calculated as negative 25. So this will be negative 25, 0, 0, 0, negative 25, 0, 0, 0, negative 25. Okay, so you add to this one. So you will get the stress tensor. So minus 25 plus 15.38. So you will get negative 9.62. Then this one you get 38.46, you get 0. So this one will be 38.46. So you are adding negative 23, then negative 25. So you will get negative 48.08. So this will be 0, then 0, 0, then negative 25 plus 7.69. So you will get negative 17.31 megapascal. So this will be the strain tensor, sorry, stress tensor. So we have converted the given strain tensor into the stress tensor. Okay, now for this stress tensor, you need to calculate I1, I2, the first invariant stress invariant, the second stress invariant, and I3. So once you calculate this, then you can write the characteristic equation for the state of stress. So calculate I1, I2, I3. So your I1 will be, so you need to add the diagonal elements, sigma x plus sigma y plus sigma z. So negative 9.62, negative 48, and negative 17. So if you add all these three things, how much you get? Negative 75 megapascal. That's correct, Michael. So then you calculate I2. So I take this out. I can just write I2 here. Okay. Negative 9.62, 38.46, 38.46, negative 48.08 plus negative 9.620, 0, negative 17.31 plus this is 31. Okay, so you write these two. Negative 48.080, 0, negative 17.31. So we can write the second invariant like this. Okay, so calculate and add up. So this is a 2 by 2 determinant. So you will be calculating the value of each determinant, then add up all these things. So I'll look for your value. I think the first determinant, when you calculate, you will get negative 1016.64. The determinant, first one, this one. The second one, so this positive 9.62 times 17.31. So you will get 832.26. I'm sorry, 166.5. So then this value 48.08 into 17.31. So you will get 832.26. So once you add up these three things, okay, and you write in megapascal square. So this is negative, these two are positive. So the final answer will be negative 17.87 megapascal square. Okay, so this is the second invariant. So the third invariant you can calculate with reference to. Okay, so I better calculate the third invariant with reference to the bottom row, because the bottom row I have two zeros, so I can take advantage of these two rows. So I3, I can just write it as negative 17.31, then the 2 by 2 determinant 9.62 negative, then 38.46, then 38.46, then negative 48.08. Okay, I can expand with reference to the third row. okay, because there are 2 zeros in the third row. So once you do this, then you will get I3. Guys, can you calculate and let me know the third invariant value? The second invariant, you can check the value will be around 17.87. That's correct, Michael. So I3, I think you get 175980. Okay, 8 megapascal square. So then you can write the characteristic equation for the state of stress. Okay, so characteristic equation. I'm sorry, mega cube. That's correct, Michael. Okay, characteristic equation for the state of stress. Okay, so sigma q minus I1 sigma square. So minus I1, so minus of minus 75, you get plus 75 sigma square. Okay, plus I2 sigma. I2 is negative 17.87, so negative 17.87 sigma minus I3. I3 is 17598. So this will be your characteristic equation for stress. All right, so this will be for part B. Then for part C, we need to calculate the volumetric strain and deviatoric strain invariance. So part C, calculate volumetric strain and deviatoric strain invariance. So this is for part C. So we know that from part B, okay, the deviatoric strain invariant is deviatoric strain tensor. Okay, we can write this as minus 10, 25, 0, 25, minus 15, 0. So 0, 0, 5 to 10 power minus 1. So this is what we got it from the part B, the deviatoric strain invariant. Okay, deviatoric strain tensor. So once you get this, then the volumetric strain will be simply epsilon x plus epsilon y plus epsilon z. Okay, so this is from the main strain tensor. So the main strain tensor is given as, okay, if you recall the question, so the main strain tensor is 5, 25, 0, 25 minus 20, 0, then 0, 0, 0. So this is the main strain tensor. So add up 5 minus 20 plus 0. So you will get the volumetric strain as negative 15 into 10 power minus 5. Okay, so from the deviatric strain tensor, you can calculate the first deviatric strain tensor, J1 dash. So J1 dash is simply you need to add these three. So as a rule, you get the deviatric strain invariant as the first one, J1 dash will be 0. So minus 10, minus 15. Oh, I'm sorry, this one is plus 10, right? Yeah, you can see the first one is plus 10. Okay, so I changed to plus. So plus 10 minus 15 plus 5, so 0. So then you can calculate the second deviatric invariant, I2, J2 dash. So the second deviatric invariant, J2 dash. So from this, you need to write the three determinants, 10, 25. So 25, negative 15, okay, plus 10, 0, 25, 0. I'm sorry, 10, 0, 0, 5, 10, 0, 0, 5. Then plus this part. So negative 15, 0, 0, 5. So guys, calculate and let me know the second deviatric invariant. So make sure every part is multiplied with 10 power minus 5. I didn't write that. So you're giving the second packet should be 10,005. Never mind. Yeah. Yeah. So if you calculate the first one, I think you get negative 775. So this one will be 50. So this one will be negative 75 multiplied by. So I can just multiply the whole thing with 10 power minus 10. So this will give me minus 800 into 10 power minus 10. So this will be my second deviatoric invariant, J2 dash. All right. So next, you can calculate the third deviatoric invariant, J3 dash. So again, use the third row. So use the third row to calculate J3 dash, the third deviatoric invariant. So I take this out. So J3 dash is, so I just take 5, then I write 10, 25, then 25 minus 15. So here, because the common multiplication is 10 power minus 15 here. So this is 5. I am just taking from the third row. Negative 387 point. Okay, 3875. That's correct, Darrell. 3875 into 10 power minus 15. Okay, so these are the three deviatric invariants. Uh, Deviatric strain invariants. Okay, J1 dash, J2 dash, and J3 dash. So the part 3, you're asked to calculate the mean stress, which we have already done, and the deviatric stress tensor. So we have already calculated this from B. So from part B, so you can just rewrite the value sigma m is equal to negative 25 megapascals. Then the deviatric strain tensor sigma dash. So you can just reproduce from part B. So 38.460, 38.46, negative 23.080. Okay, so part B, there is no calculation. We are just rewriting what you have already calculated in part B. So the mean stress and the deviatric stress tensors. So both we can just write down. So you can see this question alone took 45 minutes. We started at 8:30, then 9:15. In the exams, to score high marks, every step you need to write down clearly and try to highlight your final answers. So for example, for this type of question, part A, do it separately, part B, do it separately. So highlight your part A answers, highlight your part B answers, highlight your part C answers, like that. For every question, you need to do like that. And normally in the exams, try to do every question on a separate page. So if you do this in 2.5 pages, let us say third question, you try to do on a fresh page. And in the exams, all you're going to scan all the pages, right? So use your serial numbers for your answer papers. So particularly for solid mechanics, probably you will be using 10, 12 papers. 3 hours only in Azure. So you have only 3 hours. So therefore, write down page numbers so that when you scan, you may not miss any papers. At least we can understand that if there is any missing, if you write your page numbers. Okay. All right. So then we move on to the second question. So this is the complete answer for the first part of the question. Okay, we move to the second question. So the first two questions will be similar to your class test questions. Okay, so a material is tested under the proportionally increasing state of stress. 2 sigma 1 is equal to sigma 2 is equal to negative 3 sigma 3. Yielding is observed when sigma 3 is 100 megapascals. Okay, assuming that the material yields according to 1 Mises yield criterion, So what would be the yield stress of this material under simple tensile loading? So similarly, if the same material is used where the conditions are different, at what possible values of sigma 3 will yielding occur? So this type of question you have done for your, I think, first class test. Okay. Guys, you may just note down the values, then you can start working on this. So what is given to sigma 1 is equal to sigma 2 is equal to negative 3 sigma 3. And yielding occurs, sigma 3 is equal to 100 megapascals. All right, so I go to the camera. So this is the information given. So 2 sigma 1 is equal to sigma 2 is equal to negative 3 sigma 3. And yielding occurs when sigma 3 is equal to 100 megapascals. So you can write now from this, sigma 1 is equal to sigma 1 is equal to negative 3 by 2 sigma 3. So sigma 3 is 100. So from this calculation, you get sigma 1 is equal to negative 150 megapascals. Okay, then sigma 2 is equal to 3 sigma 3. So sigma 2 is equal to negative 3 sigma 3. So that means negative 300 megapascals. So you know sigma 1, sigma 2 values from the relationship. Sigma 3 is given. Okay, so now you can calculate the equivalent stress sigma equivalent using von Mises criterion. So 1 over square root 2. Okay, so this is sigma. So you can just use the equation sigma 1 minus sigma 2 whole square plus sigma 3 minus sigma 2 whole square plus sigma 3 minus sigma 1 whole square. So either way, because you're taking the squares, so you can write. So it will be 100 plus 150 whole square plus 100 plus 300 whole square plus minus 150 plus 300 square. So sigma 3 minus sigma 1 whole square plus sigma 3 plus minus sigma 2 whole square. So, okay. So once you do this calculation, how much is you get? That's correct, CV Cheng. So you get 350 megapascals. Okay. So this is the yield strength of the material. So this is the yield strength of the material. All right, so you can easily calculate the yield strength from this. So next part B, we need to check, find out the sigma 3 values. Okay, we take the same yield strength, but the conditions are different. Okay, so part B is the same material is used and the conditions are different. All right, so I'll take this away. So for part B, is same material is used under conditions. So here sigma 1 is equal to negative 2 sigma 2 is equal to negative sigma 3. So that means we can say sigma 1 is equal to minus sigma 3 and sigma 2 is equal to negative sigma 3 over 2. Okay, sigma 2 is equal to, so we can write 0.5 sigma 3. Okay, so now we can use von Mises-Sealed criterion. Okay, so we can use sigma y is equal to 1 over root 2. So sigma 3 minus sigma 1. So you can write minus sigma 3. Sigma 1 is again minus sigma 3. So sigma 2, sigma 3 minus sigma 2 whole square. So sigma 1 minus sigma 2 whole square. So 0.5 sigma 3 whole square plus sigma 2 minus sigma 3 whole square, that is 0.5 sigma 3 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square. So sigma 3 minus sigma 1 will be minus of minus plus. So plus sigma 3 whole square to the power of half. Okay, so guys, calculate and let me know your answer here. So this will be 2.25 plus 0.25 plus 4.0. Sigma 3 square is common. So find out the sigma 3 values from here. Any answer for sigma 3? I don't think, Michael, that is sigma 3. You will get a small value. It should be less than 350. So this is simply, I think you get, that's correct, 194.15. So you get this one is 6.5 over square root 2. Sigma 3 outside you take. So you get something like um, 1.83 sigma is equal to, sigma 3 is equal to 350. I think 1.8 sigma 3. So 6.5 over square root 2. I think root 6 over root 2. Root 6.5 over root 2. All right. So this is, now you can see we're at 9:30. We have done only the first two questions. So this is the complete working for question 2. Next, I move on to the third question. So you can see the third question. So this is a quadrilateral block of length. Okay. The dimensions of the block given. Okay. The length, width, and height. So the block is made of an annealed aluminum alloy. So the material behavior can be assumed to be rigid plastic. So the stress strain relationships are given. Sigma is equal to 300 epsilon to the power of 0.3. So we are dealing with plastic deformation. Okay, the block is loaded so that the state of stress at all times, okay, I clear this. So the state of stress is given here. So we have a stress strain relationship. And here the state of stress is given sigma z over sigma x is 0.5. Then sigma y over sigma x is negative 0.25, and the shear stress xy, yz, zx will be 0. Okay. So the load increased until a state of plastic deformation is reached. So which is characterized by uniform increase in length by 20 mm. So the length is increased by 20 mm in the longitudinal direction. So now under these conditions, we are asked to calculate the magnitude of finite strains, state of stress, state of strain, then effective stress and effective strain. So we need to calculate all these things under the given conditions. So we have basically a quadrilateral block with the dimensions given. So the stress strain relationship is given. So, and the relationship between, uh, so from here you can write sigma y is equal to, so the first one you can actually, so from here you can write sigma z is equal to 0.5. There's a minor correction here. You may just note down. So here, this is okay. So note down this as sigma y. Sigma y over sigma x is equal to uh, just give me a minute. Okay. So uh, I'll highlight this expression, then we can see. Okay, so sigma z over sigma x is equal to 0.5 into sigma y over sigma x is equal to 0.25. Okay, so from this, uh, can you tell me what will be sigma y in terms of sigma x? Can you tell me what is sigma y in terms of sigma x? Now you need to see this is 0.5 times sigma y over sigma x is equal to negative 0.25. Okay, so therefore sigma y is equal to, of course, 0.25 into sigma x over 0.5. So 0.25 into sigma x over 0.5. So that gives you negative 0.5. So you will get negative 0.5 sigma x. So can you tell me what is sigma g in terms of sigma x? Anyone? So I think CD Cheng, you need to change point negative 25 to 0.5. So you have to look only this portion. So the second one, sigma z, can be written as. So here it's quite simple. So you can write it as negative 0.25 sigma x. All right, guys, is that clear? So this is an important part in this question. Okay, you need to write sigma y and sigma z in terms of sigma x. Is that okay? Uh, see, okay, I'll just write down and okay, let me write down. Okay, I'll go back to the camera. Okay, so this is the relationship given sigma z over sigma x is equal to. Okay? So now what I'm writing is now 0.5 into sigma y over sigma x is equal to 0.25. Okay, so from this I can write sigma y is equal to 0.25 into sigma x over 0.5. Okay, so that will give you 0.5 sigma x. So 0.5 is 1 over 2. So you are just multiplying this as 2 by 1. So if you multiply this, 2.25 becomes 0.5 negative. Okay, so the second part, I can simply write sigma z over sigma x is equal to negative 0.25. Okay, so from here I can write down simply. So sigma z is equal to negative 0.25 into sigma x. Guys, is that clear? Is that okay? Heva and Darren? Okay. All right. So we can relate sigma z to with sigma x and also sigma y with sigma x. So the next one is what is given, given that under proportional loading, okay, so there is a change in length delta x is equal to 20 mm. Okay, so once you know change in length and you also know the original length, right? So you will be able to calculate the strain along x-axis. Sigma z over sigma x is negative 0.25. So the whole thing, so there is one equality here, one equality. So this whole thing is one equation. Either way, your final expressions will be the same. Sigma z, sigma y, your final expressions, you get the same. All right. So what is given that change in length was given as 20 mm under proportional loading. So therefore, we'll be able to calculate the strain in the longitudinal direction. So initial length is 100. So it increased by 20. So the final length is 120. So the strain you can calculate as ln 120 over 100. So how much will be the strain along x-axis? That's correct, Michael. So you get about 0.1823. So this is the strain along the length direction or the longitudinal direction. So 0.1823. So once you get the strain in the longitudinal direction, so next what we do is we'll write down the stress tensor. So we can write the stress tensor sigma is equal to, okay. So in the question, it was given that the shear stress xy is equal to, or shear stress yz is equal to, so shear stress zx is equal to 0. So that means all the shear stress components are 0. So therefore, we can write the stress tensor only in terms of the normal stress components. So normal stress components, we can write sigma x 0, 0, 0. What is sigma y? So sigma y you can write in terms of sigma x as negative 0.5 sigma x. Okay, so this part you can refer back here. So I'm writing sigma y is negative 0.5 sigma x. So similarly, sigma z, I can write it as negative 0.25 sigma x. Okay, so I write these shear stress components are all zero, it is given. Okay, so therefore we can write the stress tensor in 3 dimensions as like this. So everything we write in terms of the longitudinal stress. Okay, so for the given stress tensor, then you can write the mean stress. So mean stress sigma m. So mean stress sigma m is equal to sigma x plus, okay, 0.5 sigma x negative. Okay, so minus 0.25 sigma x over 3. So this is something like sigma x minus 0.5 sigma x minus 0.25 sigma x over 3. So this will give you sigma x over 12. So the mean stress, you can write it as sigma x over 12. So simply 0.25 sigma x, 0.25 sigma x can be written as sigma x by 4. So sigma x by 4 into 1 over 3. So sigma x over 12. So this is the mean stress. So once we know the mean stress, then we can calculate the deviatoric stresses. So deviatoric stresses. So sigma x dash, you can write it as sigma x minus sigma mean stress. Okay. So sigma y dash, you can write it as sigma y minus sigma m. Then sigma z dash is sigma z minus sigma m. Okay, so sigma x minus sigma m. So we can write sigma x minus sigma x over 12. So this one you can write it as 11 over 12 sigma x. Okay, so here sigma y minus sigma m. Sigma m is sigma x over 12. Sigma y, we already know the relationship. So sigma y I replace with negative 0.5 sigma x. So you can also write negative sigma x over 2 minus sigma x over 12. So you get negative 7 over 12 sigma x. So you get minus 4 over 12 sigma x. So the deviatoric stresses, you can calculate sigma x dash as 11 by 12 sigma x. Okay, sigma y dash as minus 7 by 12 sigma x, then sigma z dash minus 4 over 12 sigma x. Okay. Now the ratio of this stresses, deviatoric stresses, will be equivalent to the ratio of the strain components along y and x. So you can write epsilon y over epsilon x, the strain along x over y over strain along x is equal to the deviatoric stress over along y over the deviatoric stress along x. So we can write like this. So you know this is negative 7 over 12 and this is negative 11 over 12. So if you take this ratio, so you get epsilon y over epsilon x is equal to negative 7 over 11. Okay, so you are taking these two ratios. So this, the deviatoric stress ratios is equivalent to the strain ratios. Okay, so from this you can write the strain along y will be negative 7 over 11 times strain along x. Okay, so strain along x we calculated. Okay, so the first step we calculated strain along x. So you can calculate this as negative 7 over 11 times 0.1823. Okay, so guys, let me know the value for strain along y. That's correct, Michael. So you get negative 0.116. Now, similarly, you can also calculate sigma z over sigma x. Okay, so you can write similarly. So strain in the along z-axis over strain along x-axis. Okay, so you can take the ratio of deviatoric stress along z over deviatoric stress along x. So this ratio will be negative 4 over 11. So this will be negative 4 over 11. So that means the strain along z-axis will be negative 4 over 11 into 0.1823. So if you calculate this, then you will get the strain along the z-axis. So any answer here? Negative 0.066, that's correct. So negative 0. So this is the strain along. Okay, we already know epsilon x is 0.1823. So for part A, the answers will be the calculate the strain components. So these are the three strain components. Okay, so the important thing you need to know is that the ratio of the strains is equivalent to the ratio of the deviatoric stress components. So epsilon y over epsilon x is equal to the ratio of the deviatoric stresses along y over x. So this relationship we are applying. All right, so we can calculate the strain components like this. The next one you are asked to calculate the state of stress. So for part B, we are calculating the state of stress. So I'll take this out. So part B is state of stress. So to calculate the state of stress, we first calculate the equivalent strain. So the equivalent strain, the formula is root 2 over 3, okay, epsilon 1 minus epsilon 2 whole square plus epsilon 2 minus epsilon 3 whole square plus epsilon 3 minus epsilon 1 whole square to the power of half. So this is how you can calculate the um, equivalent strain. So 1, 2, 3 you can equate with x, y, z. So we know x, y, z is strain components. So can you calculate this and tell me what is the equivalent strain? So guys, just calculate this equivalent strain and let me know your answer. Uh, 0.18445. That's correct, Michael. So you get 0.1845. So once you calculate the equivalent strain, so we know the relationship. This is given in the question. So sigma equivalent. So we can calculate the equivalent stress now. So the equivalent stress will be 300. So 0.1845 to the power of 0.3. Okay. So calculate this equivalent stress. So any answer for the equivalent stress? That's correct, Michael. So we can write 180.7 megapascal. So once we know equivalent stress and equivalent strain, then we can use the stress strain relationship. So we can write, uh, so instead of Young's modulus, now we have the equivalent stress and equivalent strain, epsilon equivalent over sigma equivalent, sigma x minus. So we can take the Poisson's ratio as half, okay? So then minus zero point 0.5 sigma x minus 0.25 sigma x. Okay. So we so instead of the Young's modulus, we can use equivalent strain over equivalent stress. Okay, so we can apply this relationship. So sigma x minus nu. So nu Poisson's ratio is taken as half. So for plastic deformation for most metallic materials, so the Poisson's ratio can be taken at as 0.5 or half. So this is something like sigma y plus sigma z. Okay. So this is the Poisson's equation, stress strain relationship. Okay. Strain along x is for plastic deformation. Okay, instead of Young's modulus here, so you have strain equivalent over stress equivalent. So if you calculate now, you know strain is calculated along x is 0.1823. Okay, so now you have calculated equivalent strain and equivalent stress. So 0.1845 over 18.7 megapascals. Okay, so this one will be sigma x. Okay, just calculate the whole thing. So finally, you are supposed to calculate sigma x. So once you know sigma x, then you can calculate sigma y based on the relationships which we calculated earlier. So can someone calculate sigma x and let me know? Uh, 129.85. That's correct. CDChem. So you can write this as 129.8 megapascals. So then your sigma y will be, so half of this negative. So you can write negative 64.9 megapascals. Then the sigma z is 1/4 of this. So that will be negative 32.45 megapascals. So you can calculate the state of stress, sigma x and sigma y and sigma z. Okay, so you know the three values. So that means this is the state of stress. So part B, the answer for the state of stress. So you can just give the three values, 1 megapascals. Okay, this will be negative 64.9. This will be negative 32.45 megapascals. Okay, so this will be the state of stress, the answer for part B. Now, part C, you are asked to state a state of strain. So state of strain means you just include the strain components in terms of matrix. So you can just write strain matrix. Okay, so this is the answer for part C. We have already calculated the values. So you can use 0.1823 strain along X. So the shear strains are 0. So this is strain along Y. So this is the strain along Z. Okay. So this is the state of strain part C answer. Okay, so part C we have already calculated. So you need to just rewrite in the form of a matrix, state of strain. All right. So then part D is another question we have already calculated. So part D is asking you to calculate effective stress and effective strain. So effective stress, part B answer, because better to show in matrix format, Michael. So part B also you can show in matrix format. Okay, so effective stress and effective strain, both we calculated earlier. So part B, you just reproduce the answer. So effective stress is sigma equivalent. We calculated 180.7 megapascals. And effective strain equivalent is we calculated 0.1845. Okay, so you can just rewrite these two values. That will be the final answer for part D. Is that clear, guys? So this is about plastic deformation. Then I move on to the next part. So this includes the plastic movement and elastic movement calculations, and this is related to the plastic design calculations. Okay, so now let us look at this particular one. So this is where you need to calculate the, okay, the yield stress is given 250 megapascals. So the yield stress is given. So you're asked to determine the maximum elastic movement and plastic moment that can be applied to the cross section. So this is, I think, very similar to your the third assignment question. I think, and under okay. So you need to first, for plastic movement, you need to divide this area into zones of compression and zones of tension. Then you need to establish the neutral axis. So once you know the neutral axis, then you can calculate the um, plastic moment and elastic moment. So you can refer back. I think we have done very similar question for your one of your assignment question. Then I'll move on to the bottom bit. This is under plastic design. Okay. This one has minimum calculations, so we can complete this. So you can see here the frame is shown is made up of the same cross section. So there's a horizontal load acting, which is 2P. There's a vertical load which is acting P. Okay, so P is acting exactly at the center of the frame here. So the horizontal load is 2P, the vertical load is P. So you're asked to sketch all possible modes of collapse, showing clearly the locations of plastic hinges in each mode and calculate all corresponding magnitudes of the collapse loads and finally determine the magnitude of the critical load which will cause the frame to collapse. Okay? So first we need to identify the three collapse modes. So first, we only choose vertical load acting. Secondly, we choose only the horizontal load acting. And third, we choose both horizontal and vertical load acting. So in all the three cases, we clearly show the plastic hinges and we try to calculate the plastic load. All right. So I'll go back to my camera, then we'll try to draw the plastic modes, collapse modes. So the scenario given to us is simple. There's a frame. Okay. So there's a load acting, horizontal load, which is shown as 2P. And there's a vertical load acting P. So the lengths are all given in terms of L. Okay. And here the beam is connected with a pin. Okay. At the bottom here, this is connected to the ground. Okay, so this is the scenario. So we can write the collapse modes. So we can write the mode one. So this is, we consider only the vertical load. So only vertical load is acting. So we ignore the okay. So due to the vertical load, what happens is so there won't be any plastic hinge because it's been connected. Okay. So this, so there will be a plastic hinge here. So the beam will bend. Okay, there'll be a plastic hinge here. And since there will be a plastic hinge here, so the load is, so plastic load, we write it as plastic load. So we can show this is the angle theta. This is the angle theta. So now with reference to this, we will have the angle theta and theta. So so this will be the collapse mode, okay, due to the vertical load. So the plastic hinges are the three plastic hinges you have, PH, PH, PH. Okay. So there will be three plastic moments, MP, MP, and MP here. There will be three plastic moments. So the work done by the load, you can write it as PL into delta. So delta is the vertical displacement here. Okay. So then the work done by the three movements. So the work done by this movement is, so MP into theta. Okay. Plus the work done by this movement will be, this side is theta, this side is theta. So MP into 2 theta. Plus the work done by this movement MP will be MP into theta. So you will have MP times 4 theta. So we can replace delta with theta with delta over L. Okay, so delta can be replaced with L into theta. So we can write PL into L into theta. So theta, theta you can cancel. Okay, therefore the plastic load you can write it as 4 MP over L. So this is the plastic load for mode 1, the collapse mode 1. Guys, any questions, let me know. So similarly, we can write for mode 2. So we can write for mode 2. So mode 2, we choose only horizontal force. Okay. So we only take the horizontal load. So due to the horizontal load, the collapse mode will be, so there's a pin joint here, but there won't be any. So there is a horizontal displacement. So there will be a plastic mode here. There's a plastic mode, a plastic hinge, and also there will be a plastic hinge. So there will be three plastic hinges developed at the three positions here. So we have the angle theta here, we have the angle theta. Okay, so this is due to the horizontal load 2P. Okay, so in this case, we can apply the work energy theorem. So the delta is the horizontal displacement. Okay, we can write 2p into, so when the load becomes plastic load, so 2pl into delta. So this one, now you can write there's a plastic movement, plastic movement, plastic movement. So in all the cases, the displacement is angular displacement is theta. So we can write mp into theta plus mp into theta plus mp into theta. So 3mp into theta. So here delta. So again, the relationship is theta is equal to delta over L. So delta can be replaced with L into theta. So we can write 2pl into L into theta is equal to 3mp into theta. So we can cancel here this. Okay. So in this case, we can write the, okay, I'll just show here. So the PL can be written as, okay. So I take this 2 the other side, 3 by 2, okay, MP over L. So this is for mode 2. So this one is for mode 1, this is for mode 2. All right, so for the third collapse mode, we include both horizontal force and the vertical force, horizontal load and vertical load. So here you can see the plastic load is only 1.5 times of MP over L. So for the first one, it is 4 times. Okay. So here the plastic load is more. Here the plastic load is less. Okay. It is only 1.5 times MP over L. Okay. Next, the last one we'll see the third mode of collapse. So the third mode of collapse, we choose both the horizontal and vertical components. So there's a 2p and there's a p here. Okay, so the collapse mode will be due to horizontal load, there will be, then there will be, so there will be plastic hinges. Here there won't be any plastic hinge. Okay, so there will be a plastic hinge here where the load is P 2P. Okay. So here there will be a plastic hinge, and here there will be a plastic hinge. So there will be plastic movements here, plastic movement here, and plastic movement here. So here the angle will be theta, the angle will be theta. Okay. So in this case, the total work done, you can write it as 2 pi into delta plus p into delta. Okay. So we can write mp times 2 theta here, okay, plus mp times theta here. So the angle theta will be like this. Okay, here the angle theta. Okay, so you will have mp times theta plus mp times theta. Okay, so you will get 3p. I replace delta with L into theta. Okay, so here 2 theta plus 2 theta, 4 theta. So I can write 4 mp into theta. Uh, I'm sorry, I think we need to choose here the angle theta here. Okay, So therefore, this will be MP into 2 theta. So there will be 5 MP theta. So we can cancel theta, theta, then the plastic load, you can write it as 5 by 3 MP over L. Okay, so the plastic load for failure mode 3 will be 5 by 3 MP over L. So you can see from mode 1, the plastic load is 4 MP over L. Okay, from mode 2, it is 3 by 2 MP over L. Mode 3, you can see it is 5 by 3 MP over L. So which is the least among these three? Which mode is giving the lowest plastic load? Guys, can you pick up which one is the least one? So that will be the critical failure mode. That's correct, sir. So the critical failure mode will be mode 2. All right, so this is the complete answer for this part of the question. All right, so I go back to the question. Okay, so we have done the part B completely. Now I said the 4A is very similar to the assignment question, so you can work on that. Then the question 5 and 6. Okay, so question 5 is calculating the column buckling of columns. So buckling of columns. So we have done similar question. If you guys, you can attempt and you can check if your working is correct or not. If you want to know the final answer, I'll be able to provide you for question 5 and question 6. Question 6 is just we have done similar one, so for your assignment. Okay, so similar to question 5, we have done, I think in the last session under column buckling. All right, so I'll stop here. Any questions? We have a few more minutes. Let me know if you guys have any questions. Okay. So this is our last session and we'll not be meeting again. So when is your pre-exam workshop for solids? Guys, you know about your pre-exam workshop? Oh, you're not sure, Azhar? How about others? Is it online or is it Dr. Vivian is coming down? Okay, 23rd to 26th March. All right. Okay. So meanwhile, if you guys have any questions, you can always drop an email to me. Okay. And yeah, my sincere advice is pay more attention to your calculations, assignment questions. Try to understand the assignment questions well. Okay, your end of term exam questions will be something similar. Okay, and you need to practice a lot. Okay, and most likely for this paper, everybody will be getting the same set of questions. But you need to mind your working because you will not have time to discuss or do to share your answers or workings. All right. So guys, any questions, let me know. You can use your speaker or mic. Any questions, anything you want to know, you can drop an email to me. So I'll be able to provide a quick response. We'll we still get marks for the steps right if this answer. Yes, Azhar, of course you get the marks. So even if your final answer is wrong, you still get marks for your understanding, your logic. Yes. All right. So guys, then Abhay, good night, and I'll see you later. Any other questions, so you can email to me. Okay.